Hello friends, welcome to this video session of Extended Surfaces Part 2. My name is Mr. S. V. Kumbar, Assistant Professor, Sharad Institute of Technology College of Engineering, Yadra, Ichalkaranchi. So in earlier video lecture, we have studied governing differential equation for a rectangular fin, and in that case, we have studied that excess temperature theta is equal to T minus Ta, and therefore its derivative is taken with respect to x, so it will become d theta upon dx is equal to dt upon dx. If you take its derivative once again with respect to x, it will become d2 theta upon dx square, which is equal to d2t upon dx square, as ta is constant. This governing differential equation we had obtained d2 theta upon dx square minus m square theta, which is equal to 0. This is known as governing differential equation. And also we have seen there are two equivalent forms of that governing equation, that is theta is equal to c1 exponential of minus mx plus c2 exponential of mx, where c1 and c2 are constant, and theta is equal to a hyperbolic cos mx plus b hyperbolic sin mx, where a and b are constant. Now we will determine c1 c2 and a and b by applying boundary condition. Now already I have told you to calculate the set of constant c1 and c2 or a and b, we need two constants, and one constant will be the same for all the cases, that is boundary condition at x is equal to 0, t is equal to to, and second boundary condition will be dependent on different cases, right? So these are the different cases. When fin is infinitely long, second case, fin insulated at its end, that is negligible heat loss from the end of fin. Case number 3, fin losing heat from its end by convection. And case number 4, fin with specified temperature at its end. We have studied these important formulae, hyperbolic functions formulae, in earlier lecture. So we will consider case number 1, infinitely long fin. Now the question they may ask like this: from governing differential equation of fin, derive an equation for heat transfer through infinitely long fin. So here infinitely long fin of uniform cross-sectional area is shown. The fin is cut because length is not known to us. Length is infinite. So at the base temperature is T0, and at the tip temperature will be ambient temperature because its length is infinite. Okay, the governing differential equation is written as I told you, this equation was very important. We will include this derivation or this equation in all the derivations. So d2 theta upon dx square minus m square theta is equal to 0. Also we will choose its solution for temperature distribution as theta x is equal to c1 exponential of minus mx plus c2 exponential of mx. Now c1 c2 can be obtained from boundary condition. Now first boundary condition, we will apply first boundary condition here. When x is equal to 0, this is x direction. When x is equal to 0, t is equal to t0, and when x is equal to L, that is L is equal to infinity, t will be ta. These are the two boundary condition we will implement. Yes, first boundary condition, x is equal to 0, t is equal to ta, and second, and x is equal to infinity, T will be Ta, that is ambient temperature. By putting all those relation, we will get C1 and C2 value as C1 is equal to 0. Put this boundary condition in this equation. Put these two boundary condition in 6.2 equation here, right? We will get C1 and C2 value as C1 as 0, C2 as theta naught. And substituting this C1 and C2 equation back in equation 6.2, we will get theta x is equal to theta o exponential of minus mx. C1 term is omitted because it's a 0. 0 into that exponential will be 0. So theta x is equal to theta 0 exponential of minus mx. Now here rewriting that equation, theta x, theta naught is taken to left hand side. Theta x upon theta naught is equal to exponential of minus mx. But theta we had written in earlier lecture also. Theta x is equal to tx minus ta, and theta naught will be equal to to minus ta, which is equal to exponential of minus mx. Now equation this 6.3 gives the temperature distribution in an infinite long fin of uniform cross-sectional area along the length infinite length. So to determine the heat transfer rate, Q fin is equal to minus Ka dt upon dx. So this is Fourier equation when x is equal to 0, that is at base, which is equal to Kac d of dx theta x when x is equal to 0, right? Now Q fin is equal to minus Ka d of dx. So theta x is replaced here by theta naught e raised to minus mx, that is exponential of mx. Minus mx means e raised to mx. Now take a derivative of this with respect to x and put x is equal to 0. Here Q fin is equal to Kac m theta 0, because this is the derivative of theta is constant, take it outside, and derivative of e raised to minus mx will be here m into minus 1, that is m. Substituting for m, what was the value of m? That is square root of hp k into ac. So the amount of heat conducted or convected through infinitely long fin Q fin is equal to Kac into square root of hp Kac into theta naught. Again theta naught is replaced by To minus Ta, and try to simplify here. Kac square root of Kac, it will get cancelled, and the amount of heat transfer through infinitely long fin is given as square root of hp Ka, that is cross sectional area, into To minus Ta, that is base temperature minus ambient temperature. So this equation is very important, and this equation can be used to solve numericals based on fin when its length is assumed as infinite. So case number 2. So what will change here? Only there will be change in second boundary condition, right? So fin of infinite length with insulated end. Now this end is insulated if one of the end, that is right hand of fin, is insulated. So dt of dx will be 0, because hereafter the temperature gradient will not be there, because up to this end the temperature will drop, but after this there will not be any temperature gradient. So dt upon dx at x is equal to L is equal to 0. Now consider a fin of finite length L with its one end is insulated. Its thickness is T. Now the governing differential equation is written as d2 theta upon dx square with minus m square theta, which is equal to 0. This is equation 6.1. We have written this equation in earlier derivation also. Now we will choose the solution for this, that is theta x is equal to a cos hyperbolic cos mx plus p hyperbolic sin mx. Now we will solve for a and b. Now there are two constant, means we will require two boundary condition. So first boundary condition at x is equal to 0, t will be ta, and second boundary condition at x is equal to L dt upon dx, that is d theta upon dx is equal to 0, since one of the end is insulated. Okay, so from this boundary condition we will get A is equal to theta naught, and from second boundary condition d theta upon dx at x is equal to L is equal to 0. It means that we have to just derivate this theta with respect to x and put x is equal to L, and after that we will get B as minus theta 0 hyperbolic sine ml upon hyperbolic cos ml. Now substituting for A and B, we will get theta x is equal to theta O hyperbolic cos mx minus theta 0 hyperbolic sine ml upon hyperbolic cos ml into hyperbolic sine mx. Right? Now this theta 0 is taken common and take it to left hand side and do cross multiplication. We will get theta x upon theta naught hyperbolic cos ml, which is written here, hyperbolic cos mx as it is, minus hyperbolic sine ml into hyperbolic sine mx upon hyperbolic cos ml. Now here theta x upon theta naught, so this hyperbolic cos m into L minus x. From the table we have seen the formula for this, hyperbolic cos m into L minus x upon hyperbolic cos ml as it is. Rewriting the value for theta x and theta naught, we will get theta x is equal to tx minus ta and theta naught is equal to to minus ta. Now remember, tx is the temperature from at a distance x from left hand side of fin, that is from base. Ta is the ambient temperature and to is the base temperature, which is equal to hyperbolic cos m into bracket L minus x upon hyperbolic cos ml. Now equation 6.6 or 7 gives the temperature distribution, this or this. These two equations will give us temperature distribution in the fin with negligible heat transfer from its end. And in order to obtain the equation for the amount of heat transferred through this fin, we will put theta L upon theta 0, which put x is equal to L. Put x is equal to L in this equation, it will become theta L upon theta naught is equal to 1 upon hyperbolic cos ml, that is TL minus TA upon TO minus TA, which is equal to 1 upon hyperbolic cos ml. Therefore TL, that is the temperature at length L, is equal to T0 minus TA hyperbolic cos ml plus TA. This is the temperature at insulated tip. So Q fin is equal to minus K theta 0 into bracket M hyperbolic sine m L minus x upon hyperbolic cos ml. Now solving, putting x is equal to 0, solving this, we will get the heat transferred through fin is equal to KAC m theta naught hyperbolic tan h tan ml, that is putting the value for m and solving for this, very similar to previous derivation, we will get heat transferred through fin is equal to square root of HPKAC theta naught, that is TO minus TA hyperbolic tan ml, and this equation gives heat transfer rate from the insulated fin at its end. Now comparing previous equation with this equation for infinitely long fin, here one extra term is present, that is hyperbolic tan ml. Now we can see that a fin with insulated end becomes equivalent to infinitely fin when tan, that is hyperbolic tan ml, is equal to 1. So this is very important, and here we conclude today's video lecture. In the next video lecture we will see one more derivation and numericals based on fin. Thank you very much.